Axial pump. No, axial pump is a type of a pump um, that uses an axial flow. So we have here the axial flow of fluid starting from this point going here, or it can be also described starting from this point going here, and we have the discharge. So that is the difference with the axial pump and centrifugal pump. Yeah? And it is designed to handle a large volume of fluid. So the application sometimes is from irrigations mostly, no? And also from transferring of one fluid to another with a low head, no? And the difference is that between the centrifugal pump and the axial pump is that the axial pump has a low pressure discharge. Okay, so I bring down here the simple schematic diagram showing the side view ng axial pump. No? So, initially, we have here the impeller, no? And the other part, we have the stationary guide vanes, though this is mostly sometimes are being eliminated, but this is just only to improve the flow and direction of flow of the fluid. And we have the control surfaces which we are going to focus on to, and also be yung drawing ng ating velocity triangle, no? Which is the basis. Now, isolating yung part ng ating vanes. So I have here is my point 1, which is usually the entering point of your fluid, and my point 2, which is the leaving point of your fluid. Now, now remembering from our previous lecture is that the fluid entering in a moving veins, so will be mostly are the relative velocity. Now, what I have here is the relative velocity, so which is entering of the vein. So this will become my use of 1. Okay. And then now this is my absolute velocity, which is yung v sub 1. Now, do we have also the velocity, the direction of flow of the impeller? So usually this is rotating. So we have here the direction. So that corresponds to the, the circumferential, or let's say that will be the speed of the vane. So that this is a straight line moving upward. So this is my peripheral velocity, or it can be called as circumferential speed of the vane. So this is my v sub 1 prime. V sub 1 prime. So which is the circumferential or velocity of the vane. Then next we have here the normal velocity Vn sub 1. And then we have here below, so this is where my tangential velocity of the tangential velocity component of the fluid. So this is my Vt T1. Now the angle between the tangential velocity of the fluid and the absolute velocity of the fluid. So we have the representation of this one as my alpha. So this is my alpha 1. And the angle also between the relative velocity and the peripheral velocity of the vane. So I'm gonna name this one as my beta. Will be beta 1. Now at the point 2, which is leaving the vane. So again, remembering from our previous lecture, so and for the moving vanes, entering and leaving the vane will be at the relative velocity. So we have here a leaving velocity, which is the relative velocity. This is represented by use of 2. And then we have here the absolute velocity. So this will be my v sub 2, leaving the vane. And then we have here, again, the velocity of the vane, or peripheral velocity of the vane. So this will become my v1. So will become my v2 prime. So that will be the peripheral or circumferential speed of the vane. Then we have here also the velocity uh, normal of the absolute velocity. So that we have Bn of 2. Then we have the tangential velocity Bt2. So this corresponding to the tangential component, or let's say in terms ng x-axis, so ito yung corresponding x-axis niya, which changes ng BTT2. Kasi nga, from our previous lecture, so we are dealing only on the horizontal and x-axis, but now since we are rotating, so we change yung uh, velocity at the x-axis is being replaced by tangential velocity since ang bane natin is now in a rotating motion. Then we have also the angle in between the absolute velocity and that your tangential velocity. So I'm gonna name this one as my alpha 2. And in between also, pagitan ng ating relative velocity and also the velocity of the vane. So this is will be my beta 2. Okay, so yung absolute velocity natin na v sub 1 is also equal to your v sub 2. Now, we can combine this velocity triangle in such a way that mas madali natin siyang isolve at mas madali natin siyang tignan, no? So, just let me try to do that one, no? I'll show you. So, just combining or redrawing it in just in one figure, those velocity triangle in just one. Okay. Okay, so this is representing yung point 1, no? Now, since yung velocity, yung absolute velocity natin, which is yung leaving from the vein is equal, so we can draw this one uh, parallel on this side, no? So let's try to do that. Okay, so I made the corrections na lang, no? Since relative velocity natin inlet is also leaving is the same, so that must be parallel sila, no? So we have here just to um, not actually a parallel one, but just only to show the representation of this one of the ano. So it can vary kasi pa rin yung angle dito at angle of beta 2, no? Just a proper representation. Okay? So it will be vary sooner or later depending doon naman sa given sa problem. Okay, so this is the representations which is much easier to solve comparing on this type of representations. This is much easier comparing on this one which is separated. Now combining this one, we may able to mas maganda siyang uh, in terms of representation of the velocity triangle, so we can easily distinguish. Okay, it's just only to combining the inlet and outlet, no? Now for the power ng uh, ng call this ng axial pump. So again, we start with your equation PW, so that represents the full power. So this is equal to your angular velocity times your torque, no? Where yung torque natin, so this is expressed as my force times my the radius. So that will be the distance or yung arm ng force, no? Now yung force again, so this is equal to your density, volume flow rate, and from the previous lecture, so that will be the velocity, change in velocity. So there will be velocity 2x, we have your velocity 1 of x. So the change in velocity. Okay? So since now meron na tayong, since from the previous lecture, this is represented as x, since we have x and y axis. So we're going to change this one as your tangential velocity since we are in rotations, no? So rotating, so the velocity, no? So the velocity, no, is already in tangential if this is rotating, no? Okay, so we have the yung tangential velocity, so referring to the figure, no, at point 1. So on tangential velocity natin, so that will be represented as your BTT1. Okay, so let's try to go back to equation. So I'm gonna, that will be BTT2, sorry. So the tangential velocity at call this 2, no? So let's try to substitute that one and change it to BTT2, and also yung corresponding, that will be BTT1. Now, substituting this one to your torque, so this one, so we have your torque is equal to the radius, no? And that will be multiplied to my density, volume flow rate, and we have your VTT2 and VTT1. Now, since we have the location of your, call this the diameter, no? So we have your inside and outside diameter, no? So we can change this one to your torque. So we'll become as distributing this one. So that will be density, will be rate, and this is my radius 2, and velocity tangential 2, and this is my radius 1, no? Times the velocity tangential 1. Now, we have the torque and substituting this one to my power. So, rewriting yung power natin. So, we have your power. So, that will be the angular velocity times your torque. Or let's say that will be angular velocity times the value ng torque. So, that will be density, volume rate. That will be radius 2, tangential velocity 2, and that will be radius 1, tangential velocity 1. Okay, close parenthesis natin yan. Now, yung angular velocity natin, so, or let's say that will be the velocity, no? So that will be the velocity of the vane, v1 of prime, which is equal to the velocity, uh, well, this velocity 2 prime is equal to your velocity prime. So that will be the velocity of your vane, no? So that will be the peripheral or the circumferential speed of the vane, no? And ang b sub 1 prime natin, so that will be equal to your radius 1 times my angular velocity. And yung velocity 2 naman natin, prime, is equal to your radius 2 times my angular velocity. Now, from this equation, so substituting natin yan, so we multiply in those equations, substituting that one, so we are power. So since this is, we try to rewrite pala natin, no? We can rewrite yung angular velocity. Since yung angular velocity is the same inside and outside diameter of the vane, so we can rewrite your angular velocity as your may velocity of the vane prime divided by my radius 1. And sa loob naman, o yung outside, 2, that will be equal to velocity 2 prime divided by my radius 2. Now, substitute natin this in equation ito from your equation, so we can rewrite your angular velocity. So, values nito, which is this one, multiply natin doon, or let's say these values. So, that will be the density, the volume flow rate, and this is the radius 2, tangential velocity 2. So let me change this one as a bracket. So that will be radius 2, tangential velocity 2, multiplied with the angular velocity, that will be velocity 2 prime, divided by my radius 2. Okay? And minus, no? So that will be minus my radius 1, tangential velocity 1, and multiply by the velocity 1 prime divided by radius 1. So bracket this one. So eventually, it will be cancelled out. Yung common dito, ito. So let me cancel this one, and this one, and this one. Okay. So we can rewrite now your power. That will be density. So this is tinatawag nating the water power or water horsepower. So this can be called as your water HP or water horsepower, no? So that will be density, volume flow rate. So this is multiplied by my tangential velocity 2. We have the velocity of the vane at point 2 minus my tangential velocity 1 times my velocity of the vane inside or yung point at point 1. Okay, then close parenthesis. So this will become now your water horsepower. So finally, we have already the values of how to compute yung water horsepower, no? Now let's go to the head, no? The head. So that will be or that is equivalent the pressure discharge or yung how much is the capacity that uh, the amount of volume can be delivered by the axial pump, no? So let's compute or uh, call this derived equation for your head or your total dynamic head, which is sometimes called a total dynamic head. Now for my head, so that will be, let's start with the equation. Your water horsepower can also be expressed, no, as my density, gravity, and we have your volume flow rate, and this is multiplied with your head, or it can be expressed as a TDH. So sometimes it is called TDH or total dynamic head, where density and gravity, so combining this one is equal to the specific weight, no? So we are merely concerned with your head. So let's rewrite your equation. So that will be water horsepower divided by my density, gravity, and my volume flow rate. Okay. So remembering yung kanina, no, from our previous equations that our watt or horsepower is expressed on this form. So that will be density, flow rate, and velocity. Okay, so let's try to substitute that one. So equation. So we have, so let me just draw a straight line here to represent yon. So that will be um, density, no? So density, volume flow rate. So bracket natin to, we have your tangential velocity 2 times my velocity of the vane prime, 0.2, and tangential velocity 1 times my velocity of the vane at leaving, no? This is leaving the vane and this is entering the vane, so that will be v1 prime, close, okay? And this is divided by the density, gravity, and we have the volume flow rate. Now, since we have here the common, so we have the density, this one, and this one, your volume flow rate will be cancelled out. So fine, and we can rewrite now your equation as your tangential velocity 2 times my velocity of the vane, and it will be minus my tangential velocity 1 times my velocity of the vane, and this is all over divided by my gravity. So this is the general form, no? General form, no? Now, referring to the velocity triangle, let's try to refer to the velocity triangle to get the other values of this one, no? Now, referring to our velocity triangle, okay? So, referring here, no? So, yung values, so we have yung BTT2, okay? So, this is your BTT2 with a given angle, your alpha, no? So, we can use a cosine law, cosine. So, that will be the cosine. So, cosine of your alpha 2, so this is equal to your opposite, so that will be BT T2, no? So that will be BT T2, and this is all over. You have your hypotenuse, which is your absolute, okay? So, which is given, then we can rewrite yung value ng BT T2, which is equal now to your absolute velocity. Sorry, this is 0.2, no? So, let me change this one. Sorry, it will be 2. Now, yung absolute velocity natin, this is equal to your absolute velocity 2. Since yung value niya, what is entering to the vein and leaving to the vein is the same amount of volume. Okay, so that is equal yung absolute velocity at 0.1 and also the absolute velocity at 0.2. So my absolute, so I can say now my tangential velocity 2 is equal to absolute velocity times my cosine of my alpha 2. And we can substitute here to the equation so later on. So kunin din natin yung tangential velocity ng 0.1. And let's try to do that one. Again, so this is cosine, no? So for this side, so that will be cosine of my alpha. So that will be yung opposite mo. That will be that adjacent mo, sorry. That will be tangential velocity 1. And this is divided by my hypotenuse. So that will be um, velocity, absolute velocity 1, or we can say that the tangential velocity 1, so that will be the absolute velocity 1 times my cosine of my alpha 1. No? Now, yung values natin here, substituting to our previous equation, so we can rewrite your head value. No? So, change natin to. So, I can say that my head, so that will be yung value ng tangential velocity T2, so that will be the you call this velocity, sorry, this is velocity 2 times my cosine of alpha 2. So this is multiplied by the velocity of the vane, 0.2, and minus my absolute velocity 1 times my cosine of alpha 1. And this is multiplied with your velocity, no? Prime. And all over divided by the gravity. Okay. Now, we have made already yung general for another form ng head, no? Now, let's make the another variance to compute the head. Now, we're using the angle beta naman on this side. So, you will notice dito, we have the tangent, no? So, we have your tangent of my beta 1. So, for my opposite, so that will be the normal velocity. Okay, let's try to solve muna natin yung sa point 2. So, I'm gonna change this one at point 2. So, tangent of beta 2. So, yung opposite mo, we have the normal velocity 2. And this is over with um, the adjacent. So, that is the velocity of the bane at point 2 minus the tangential velocity bt B2, BTT2. So tangential velocity of the fluid. Okay. So rewriting this one. So we have the velocity of the velocity of the vane, sorry. Then we have the tangential velocity of the fluid. So this is equal to the normal velocity. Then this is over with the tangent, no? Tangent of beta 2. Or we can say, rewrite this one as my velocity of the vane, tangential velocity 2, or this will be as your, so this is normal velocity 2, and this is cotangent of my beta 2. No? So, by manipulating your equation, so we have your BTT2, so this is equal to your velocity of the vane at point 2 minus my normal velocity times my cotangent of beta 2. Now, referring naman doon sa point 1 sa entering, so you will notice here yung tangential velocity natin makes an angle with your alpha 1, where your hypotenuse is or sorry, makes an angle alpha 1, and where your opposite is your normal velocity at point 1. No? So let's write the equation for this one. So we have that will be tangent of my alpha 1. So this is equal to your opposite. We have your normal velocity at point 1 and your adjacent. So that will be the tangential velocity 1. And we can rewrite this one as your tangential velocity 1 is equal to your normal velocity 1. Then this is divided by the alpha 1, or let's say this is normal velocity 1. So this is normal velocity 1 times my cotangent of your alpha 1. Okay? So, going back doon kanina from this equation, no? So that is the tangential velocity, diba? So, but the value my tangential velocity, so that will be the absolute velocity times my cosine alpha. So, equating that one, so that will be uh, velocity, sorry, so that will be velocity, so velocity, absolute velocity 2 times my cosine of alpha 2, which is equal to the velocity of the vane at point 2 minus my normal velocity 2, then multiply by the cotangent of beta 2. Okay. So, notice this one, no? Yung value ng velocity 2 cosine of alpha 2 is already equal dito. Yeah? So, we can substitute that one doon sa value na hen. So, later on, we'll try to do that one. Then, uh, For the other side, sa point 1, so again, we can also substitute yung values nito ng files, ito ng value ng tangential velocity, no? So let's try to apply that one. So you will notice here the value ng tangential velocity at point 1, so that is equal to the absolute velocity times my cosine of alpha. So substituting that, equating that one dito, so that will be rewriting your equation here. So we have your tangential velocity, sorry, check this one. So absolute velocity 1, so that will be cosine of alpha 1, which is now equal to the normal velocity 1 times my cotangent of alpha 1. So notice this one. So this will be absolute velocity 1, cosine of alpha 1. So check natin dito. So that will be equal dito, no? So velocity 1, absolute velocity times my cosine of alpha 1. And yung value na ito, we can substitute yung value ng uh, equating natin ito. So let's try to apply that one. So from the head, so coming from this equation, so I can say that my head now, so my head now is equal to the velocity 2, which is equal dito, so that will be the velocity 2, velocity of the vane minus my normal velocity 2 times my cotangent of beta 2, and this is multiplied by the velocity of the vane 2 at point 2, so that will be minus, so value nito, so ito yon, so that will be the normal velocity 1 times my cotangent of alpha 1, then times the velocity of the vane, point 1. And this is all over divided by the gravity. So noting that na yung ano natin, yung that the velocity of the vane at point 1 ay point 2 and velocity of the vane at point 2 are equal with the velocity v prime. So velocity of the vane. And also that my normal velocity 1 is also equal. So let me change this one, where my normal velocity 1 is also equal my normal velocity 2, and this is the normal velocity. So I can write now or rewrite yung equation natin as your head. So this will be the velocity, no? Minus my normal velocity times my cotangent of your beta 2, and this is multiplied by the velocity of the vane minus my normal velocity times my cotangent of your alpha 1 times my normal velocity of the vane, and this is divided by the gravity. So furthermore, so transpose distributing here, that will be velocity of the vane, that will be squared minus the normal velocity times my cotangent of beta 2, and this is velocity of the vane minus uh, that will be the normal velocity cotangent, and we have your alpha, and this is velocity of the vane, and this is divided by the gravity. And we can rewrite this one, and we can simplify, no? Simplifying the equation. So that will be velocity, this is squared, velocity beam squared, minus, we can factor out also the normal velocity dito. So let's say this will be velocity of the vane times, so this is over. So let's try to, this is over with the gravity, divided by the gravity. And ito, that will be times with the normal velocity. We have your cotangent and beta 2. And this is over with your gravity. And this is the normal velocity, cotangent. We have your alpha 1 and velocity of the vane. And this is all over with your gravity. So finally, we can factor this one. So we have your head. So that will be velocity. No? So that will be velocity of the vane. That is square. And this is all over with your gravity. And pwede natin i-factor dito, which is yung common. That will be the velocity of the vane and velocity of the vane and also your gravity. So that will be velocity of the vane. This is over with your gravity and multiply this one by the normal velocity and times my cotangent of your beta 2 plus cotangent of your alpha 1. Okay, so we have here the general equation. No? So that will be the head velocity of the vane squared divided by the gravity velocity of the vane times the normal velocity and the gravity, then multiply by the cotangent of beta and cotangent of alpha. Now, when the ideal absolute velocity at the entrance alpha is established by the fixed vane or stator, or if there is no free rotation, where the angle of your at point 1, let's say angle alpha is 90 degrees, the theoretical head relation changes. No? So my head, if you will substitute the alpha 90 degrees, so eventually the tangent or cotangent of alpha is 0. So mangyayari dyan, our equation changes into that will be the head. No? So that will be the velocity of the vane. So this is square divided by the gravity minus my velocity of the vane times my normal velocity, and this is divided by the gravity, and this will become multiplied with the cotangent na lang ang may iwan. No? So it will be cotangent of your beta 2. No? So that is if there is if there is a fixed vane lang naman. So this happens if there is a fixed vane guiding yung entering ng fluid to the envelope. Again, so I would like to clarify, no? So alpha 1, 90 degrees lang. Now, if that changes yung angle, if let's say mga 30, 40, so may value pa rin siya. So it does not mean that if there is a stator vane, so yung sinasabi kasing stator vane, so ito yun, no? So let's try to zoom on this one, yung figure earlier, no? So ito yun. Yan, no? So, yung sinasabing stator vane, so ito yon. Okay? So, which is does not move. So, meron kang shafting dito which is rotating, may bearing lang yan sa gitna, and this is become the stator. Now, usually, ang sinasabi niya doon, if there is a stator vane before, no? Before the uh, rotating vanes o yung impeller ng axial pump. Now, if the angle is 90 degrees, so eventually if you will to substitute that one to 1 over the tangent of alpha, eventually the value will be 0 out. Now if there is value, let's say which is not eventually mag-equal to 0, so hindi pa rin magbabago yung equation mo, the same pa rin siya, which is ito pa rin, no? So ito pa rin ang gagamitin since ito hindi naman nag-0. Okay, so we'll still be using this one, no? So ito lang yung another call this definition, no? If there is no free rotation and the angle alpha is 90 degrees, so eventually plus mo yan, eventually the value will be 0 out, and you will be come up with the using this equation. Okay, so let's have a sample problem, no? An axial flow pump is designed with a fixed vane or stator blade located at the upstream, of the impeller. The stator imparts an angle of 75 degrees, that will be your alpha 1, to the fluid as it enters the impeller region. The impeller has a rotation speed of 500 rpm with a blade exit angle of 70 degrees. The control volume has an outer diameter of 300 mm and the inner diameter of 150 mm. Determine the theoretical head rise and the power required if 150 liters per second of liquid with a specific gravity of 0.85 is to be pumped. So I bring down here, I rearrange the drawing nung previously. So usually yung pinakauna we have here, from the previous, yung stator is located at the back. Now, as the problem says that the stator is located at the upstream, so ito yon. Now, the stator is imparting the fluid at the angle of 75 degrees. So, it does not mean na magzi-zero out na yung alpha. Yung alpha. So, we have the value of your alpha. So, the equation that will be used to determine the head rise, so again, we'll be using this equation since yung alpha mo is not zero. So, let's try to draw naman yung velocity triangle of this axial pump. Now, based on the given, so sabi do sa problem, we have the angle of 75 degrees, so which is imparting from by the stator. And then the fluid enters the region, so we have the rotational speed. So that will be the RPM, so yung ikot ng shafting, or ikot ng buo, So that will be an angular, so that will be the N, and that will be the RPM, which is 500 rev per minute, So that will be the rotation of the impeller and the shafting, And then has a blade angle problem, which is 70 degrees. So here the blade, that would be 70 degrees. Okay. And control volume, so we have the outside diameter, which is 300 mm, and an inner diameter, which is 150 mm. Okay, so we need to determine the theoretical rise where the volume flow rate, so that will be the volume flow rate. So this is the flowing here. So we have the volume flow rate, which is a value of 150 liters per second. So that is entering and leaving the vein. So that will be how much of the volume being displaced by the axial pump. Okay, so we specify already the given. So imparting angle 75 degrees and leaving angle, it will be 70 degrees. Now, from the given equation of your head, now we have already established yung angle. Now we have the 70 degrees and your alpha, so we have the 70 degrees. So, ang wala na lang natin is the velocity of the vane and the normal velocity. Now, to solve the normal velocity, my given volume flow rate, so that is equal to 150 liters per second. So this is equal to the area, and times the normal velocity. Or we can express this one as your area, so that will be pi over 4 and multiplied by the diameter outside, so that will be squared minus your diameter inside, and this is square, and this is times with your normal velocity. So substituting in order to get, or let's say rewriting your equations here, so I have my normal velocity, so that will be 4, 4 times the volume flow rate. So that will be, we have here the pi, no? So that we multiply by the outside diameter squared minus your inside diameter squared. So my normal velocity now is substituting the values, that will be 4 times the volume flow rate, which is 150 liters per second. And this is divided by pi, and close bracket natin to. So that would be the outside diameter, which is 300. So we have 300, and convert that one in meters, so it will be 0.3. So meter. So square this one minus that will be 0.15 meters. Square this one and close bracket. So my normal velocity is equal to 2.83. So this is meter per second. Okay, so we have already the normal velocity. Next, we need to find out, so what is the velocity of the vane. Now, since we have a two diameter for the we call this inside and outside diameter of the vane, will be try to average the radius, no? So to compute the velocity of the vane, so we have the velocity, so velocity of the vane. So that will be equal to your angular velocity now times the average diameter. So that would be the diameter outside plus diameter inside. And this is divided by 4. Now substituting values here. So we have, so that will be the velocity of my vane. So where your angular velocity, so that will be 2 phi, no? So this is can be expressed. So let's try to express this one. Will be 2 phi n. So times my outside diameter plus your inside, and this is by 4. So we have here 2 phi, no? And your n, so that will be how much is 500. So this is 500 revolution per minute. And convert this one. So, convert natin yan. That will be 1 minute is 60 seconds. And multiply it with the change in diameter or the average diameter. So, we have the outside that will be 0.3 meter plus the inside that will be 0.15 meter. And this is divided by 4. So the velocity of my vane now is equal to 5.89, that will be meter per second. Now, we have already the velocity of the vane, so substituting it here from our head, no? So we can rewrite this one as, it will be my head, which is equal to the velocity of my vane, so that will be 5.89. This is meter per second. So square this one, and this is divided by the gravity, which is 9.81 meter per second. So minus the velocity of the vane, which is 5.89, so meter per second. Again, divided by the gravity, which is 9.81 meter per second. Then multiply this one by the normal velocity, which is 2.83 meter per second. And multiply it by the cotangent. So we have the cotangent, or let's say we can express this one as 1 over my tangent. So that would be 1 over my tangent of the value of your beta 2, where the value of beta 2 is 70 degrees. Then plus the value of your alpha, so that would be 75. 1 over my tangent of 75 degrees. So my head now is equal to 2.46 meters. So that will be the rise of head, or how much is the pressure being discharged to of the axial pump. Now to determine the power, the power required or yung tinatawag nating that will be the water horsepower. So change this one. So that will be water horsepower. So this is simply as your multiplied by your density, no? Density, gravity, and density, gravity, and we have the volume flow rate, then times the head, or let's say this is your total dynamic head. Now, since we have this, okay, so that will be the power required or water horsepower. Now, you will notice there that we have the specific gravity of your water. Now, remembering the equation for the specific gravity, so specific gravity, so this is Sg, so it can be expressed as the density of your fluid divided by the density of your water. No? So we can say that density, or let's say the density of the fluid, density of the fluid, so that will be the specific gravity times the density of your water. So this is the density of your fluid, so I can rewrite my water horsepower as my density of my fluid, so times, sorry, that will be specific gravity, sorry, let me change this one, specific gravity times the density of the water. So, yon. Then, multiply with the gravity and the volume flow rate and your head. So, my water horsepower will become now, that will be 0.85 for my specific gravity, multiply density of water, that will be 1,000. So, this is kilogram cubic meter. Then, the gravity, that will be 9.81, that will be meter per second squared. Then, multiplied by the volume flow rate. So since that is 150 liters per second, so we need to convert this one to cubic meter. So this is 0.15, no? 0.15, that is cubic meter per second. And multiply by the head rise, so that would be 2.46 meter. Okay, so this is equal now to the value of your water horsepower is that will be 30, no? 3076.9. So this is Newton meter per second, or let's say this is uh, equal to 3.1. So I can say this is equal to 3.1. So this is the units of kilowatt. Okay, so that concludes the solution of the problem. So, madali lang naman siya. So, it's not complicated comparing with the centrifugal pump. Okay.